Have you ever sat at a table eating an apple and wondered, hey, don't waves need a medium in order to travel? Well, since we know that light behaves like a wave, physicists assumed that, like other waves, light needed a medium in which to travel. This medium was termed the luminiferous ether, or, like we like to call it, just the ether. Now, this medium was transparent, so it wasn't readily observable, but was presumed to fill all of space. By assuming this, the ether was stationary and created an absolute reference frame for the universe. Now, a physicist by the name of not Albert Einstein, but Albert A. Michelson, sought to prove the existence of this ether and proposed a way to do it. Michelson invented an instrument known as the Michelson interferometer. Yeah, I know, he named it after himself. Everyone does. Now, the way that this instrument was built was that it had a monochromatic light source that is right here that shoots that light to hit a half silvered mirror over here. Half of that light source would hit the mirror and travel a distance of L2 to a micrometer adjustable mirror. The other half of the light source would travel through the non-silvered portion of the mirror and travel a distance of L1 to a fixed mirror. And between that fixed mirror and the half-silvered mirror is a compensating plate, which has the same material and thickness as the mirrored plates. This plate is used so that both beams of light end up passing through the same thickness of glass. These two waves are then reflected by the respective mirrors and sent back to the half-silvered mirror, and the two waves of light meet up and travel to the detector. And then, once the detector reads it, it displays what are called interference patterns. Now, when these two waves meet back at the center, they can be in either phase or out of phase. Now, an in-phase situation is when the two waves are perfectly synced up and end up creating constructive interference. Now, constructive interference is when the waves actually add each other's amplitudes together, creating a situation like this. Now, when they're out of phase, in this case, perfectly out of phase by 90 degrees, they actually cancel each other's amplitude out, which just results in a flat line. Now, this detector would show bright and dark bands to represent these interference fringes. And as these wavelengths changed their phase shifts, so would the interference fringes. Now, I'm going to talk a little bit more about the math behind this apparatus. It'll be a little complicated, so I've just given the simplified version, taking out all the algebra steps. Now, the beam of light that would hit mirror E was in the direction of Earth's velocity, while mirror C was perpendicular. In reality, this meant that the apparatus actually moved along the path of the Earth, and that the path that the beam took to hit C was actually C prime. And then it would go back down to the half-silvered mirror B, but it would have a new position B prime because it would move in the direction of Earth's velocity. But the beam that would go to mirror E, which in this case is now E prime because it as well moved in Earth's velocity's direction, remains unaffected because the mirrored distance remained the same since they both moved at the same speed. Now, the time it took for beam 1 to hit mirror E and return to the half-silvered mirror B was 2 times the distance between the mirrors B and E, denoted L1, divided by C, which is the speed of light. And then all of that divided by 1 minus v squared over c squared, where v squared is just the velocity of the Earth. The time it took for beam 2 to hit mirror C prime and return back to B prime was similar to the first beam, but instead the denominator is rooted, and it uses the distance from mirror B to C denoted L2, instead of in the first case where it was L1. Now, the difference in time of those two beams hitting is equal to 2 over c, the speed of light, multiplied by L1 times 1 plus beta squared, minus L2 times 1 plus beta squared over 2, where beta squared is just the Earth's velocity squared over the speed of light squared. Now, after you rotate that instrument 90 degrees, the equations become switched for T1 and T2 and become T1 bar and T2 bar. The only difference now is that L1, which was originally going parallel to the Earth's velocity, is now perpendicular, and L2 is actually now parallel. So the delta T bar is actually similar to delta T, but instead now L1 and L2 have switched positions in the equation. So subtracting delta T bar by delta T gives you the finalized equation of 1 over c, the speed of light, multiplied by the addition of L1 and L2 times beta squared. And remember, beta is velocity squared over c squared. Now, delta x, which is the shift in interference fringes, is also the difference in the wavelength's phase shifts. Now, if you bring c up to that delta x in the equation, you can have c multiplied by the delta t bar as well as c multiplied by delta t, which gives these new symbols delta d bar and delta d, which is actually just the phase shift of each position in the apparatus. So delta d is the phase shift of the two wavelengths when the apparatus was not rotated at all, and d delta bar is the phase shift of the two wavelengths when it was rotated 90 degrees. Now, in order to calculate the amount of fringes, it is delta d bar minus delta d over lambda, which is just the wavelength. So, now that the math is out of the way and getting back to the subject at hand, the theory to this experiment is that you're measuring the speed of the Earth through the ether and that the velocity of the Earth was known. So the wavelength was 600 nanometers. The length between the mirrors were both 11 meters exactly. Again, the velocity of the Earth was known to be 30 kilometers per second, and the speed of light, which is 300,000 kilometers per second. So first, we calculate the beta squared value, which is 1 times 10 to the negative 8. Then we calculate the delta x value, which ends up being about 0.37, which is the amount of fringe change we're expected to see. Now, once the experiment was actually conducted, they found out that their actual n value, which is the change in the fringes, was 0. Now, that's not just the weird thing, but they took the data from every rotation of 360 degrees, not just at 0 and 90, and again, n equaled 0. So that means no shift. Now, the ether advocates refused to accept this, and they urged Michelson to repeat the experiment on a grander scale. Together with Edward W. Morley, a larger instrument was conducted, and this device had a path length that was 10 times larger than the first instrument. This device should have given a fringe shift of, again, 0.37, but instead only observed a 0.05 5 shift. So this again proved the negative result. Well, this still wasn't good enough. So over the next 40 years, this experiment was conducted with even greater precision. But still, looks like there's just no ether.